Sharing is not Yes, sir. Now you can share it, sir.
Okay. In between, you have to take care because yesterday I saw many times. No, I was not able to. You are muting no completely, so I am not able to know contact with you. So take care that I'm unmuted. Huh? That on that alone you can take care.
Okay, sir. Thank you.
You are able to see the screen, right? Shared screen.
Yes, sir. Yes, sir.
Thank you. Yeah, good.
Good afternoon, sir. Good evening, sir. Balaji, sir. Good evening, sir.
Very good evening.
Shall we start, sir?
Yeah. I'm ready.
Yeah. Thank you. Thank you. Dear sir, madam, we are entering into day 3 of online ATAL 6-day faculty development program. Session 5, Industry 4.0 Trends, Future Technologies Shaping Manufacturing by Dr. Balaji Venkatraman, sir, President, TVS Sensing Solution Private Limited, Madurai. In this August occasion,
meeting is being recorded.
I invite Dr. S. Ganesh Kumaran, sir, Associate Professor, Department of Public, to introduce our resource person. Good evening, sir. We are happy to introduce the guest, Dr. Venkatraman, sir. It is my distinct privilege to introduce our esteemed resource speaker, Dr. Venkatraman Balaji, sir, the President of TVS Sensing Solution Private Limited and Director of Fiber Optic Sensing Solution Private Limited. Dr. Venkatraman Balaji, sir, has had a distinguished academic and professional journey. He completed his BE in Mechanical Engineering in 1991 and ME in Industrial Engineering in 1997 from Tyagaraja College of Engineering, Madurai. He further earned his PhD in Mechanical Engineering in 2020 from Kalasalingam Academy of Research and Education. Dr. Balaji sir career began in 1985 when he worked with L&T Limited, serving as a project engineer. He was involved in the erection and commissioning of cement and fertilizer plant across Maharashtra and UP. His entrepreneurial spirit led him to own a small-scale sheet metal industry from 1988 to 1997, followed by a role in TVS Private Limited, where he worked in corporate planning from 1998 to 2007. Sir worked as a role of head marketing sales in TVS Cherry Private Limited and later head of the export division. In 2007, Dr. Balaji became the president of TVS India Private Limited, a position he continues to hold. Throughout his career, Dr. Balaji sir has made significant contribution to the field with numerous published papers in SCI, Scopus, and international journals. He has traveled extensively for business and training, visiting many countries such as USA, UK, Germany, Italy, France, Switzerland, Czech Republic, Canada, China, Hong Kong, Taiwan, Malaysia, Singapore, Sri Lanka, Dubai, and Japan. It's a truly an honor to have him with us today, and we look forward to the valuable insights he will share with us. And happy to hand over the session to Balaji sir.
Thank you.
Thank you, sir.
I'm just skipping this slide. This is about TVS Sensing Solution, where I belong to. We are in the field of products in switches, sensors, solenoids, and electronic component carriers for 80% into automotive and 20% in industrial solution field. We also have a subsidiary called Fiber Optic Sensing Solution, which is in the field of so providing solutions in intrusion detection systems for digital corridors, in the border, India border and oil and gas, such kind of premium segments. So today's topic is going to be Industry 4.0. Uh, this is called, otherwise like some places, it's called a kind of smart factory, and in some countries it is called, like Germany and all, they call it as European countries call it as Industry 4.0. American world called it as a kind of more smart factory, and the research world call it as CPS. So different names, but it all means the same thing. It's a kind of interconnected things. Okay, so what we'll do is we'll deal the whole subject into. See, for want of bandwidth, I'm going to put off my video. Whenever it is necessary, I'll come back in the video again. And today's session, we'll classify them into 4 parts. I'll start with introduction, what is Internet of Things is all about, followed by general applications and industrial applications in specific. After explaining that, after we understand thoroughly what is the Internet of Things, we'll also get into a shop floor case study. I have 3 shop floor case studies. Depending on the time, I will take 1 or 2 or 3. It all depends on the time, how much we are going to spend on them. Finally, we'll conclude the subject by stating the key benefits and future scope. So first we'll start with the introduction. Let me start from the basic, even though today, I think 5 years back when I used to deal this subject, many people don't know what is Industry 4.0. But today, I think this has become a kind of common word, at least definitely in the academic world, I think people know what it is. Still, for want of, I would say, complete subject to be dealt, I'm starting from the basic, but quickly I will go through. What is Industry 4.0 is all about. Industry 4.0 or the 4th Industrial Revolution is a collective term embracing a number of contemporary automation, data exchange, and manufacturing technologies. So it has gone through kind of 200 years plus of history. Industry 1.0 talks about the mechanization with steam power and weaving loom. Now that's the way the whole thing mechanization has started in late 18th century, 1784. Exactly 100 years later, Industry 2.0, there is a mass production, assembly line, electrical energy is invented. All such things have started happening. Okay, that is somewhere around at the 19th century. And in 1969-70, Industry 3.0, which involves automation, computers, and electronics. So in a way, you can say that steam, then mechanical, then it's all electronics, right? That's the way Industry 1.0, 2.0, and 3.0 are described. And today, we are in Industry 4.0, which is called cyber physical system, Internet of Things, smart factory, whatever you call, all denotes the same thing. Okay. Another definition, this is the manufacturing side of digital transformation. When you say Industry 4.0, when you say CPS, cyber physical system, it can be anywhere. And when it is applied in industrial setup, then it is called Industry 4.0. So the tantalizing potential of smart factories that deliver intelligence on demand. What it constitute, Industry 4.0, you can see here, the Internet of Things, big data analysis, analytics, cloud computing, cyber security, horizontal and vertical integration, robotics, augmented reality, additive manufacturing, simulation, all are part of this Industry 4.0. So there are some basic questions. Is it different to M2M? No, M2M is a subcategory of when IoT. After IoT is evolved, I think all other things, in the automation, whether it is mechanical, electrical, electronics, software, all of them have become subsect of Industry 4.0. So, was smart factory, whether it is different from is Industry 4.0? No, it is related to smart manufacturing. Okay, so it's just how you call in different regions of the world. So the strong definition for IoT or Internet of Things, you can see that the T stands with the capital H always. So that's the way you have to write it also, Internet of Things. Internet of Things is a concept of connecting any device to the Internet and to other connected devices through either wired or wireless networks, exchange of information and knowledge for new value creation. This is most widely accepted definition. Though there are many definitions available, this is the most accepted definition, I would say. So when we say things, we are talking about the devices. How this kind of invading or penetration of devices happen over a timeline. If you see between 2010, every human being, the population, first you see the people are denoted by a kind of orange color and devices is denoted by blue color. You can see the size of the bubble, what has been put at the bottom. In 2010, it was 1.83 connected devices per person on this globe. Every person used to have two connected devices somewhere. We'll later get into that. Anything, the connected devices, when you say a smartwatch is a connected device. I would say refrigerators, smart refrigerators, you can call them as a kind of connected device. Likewise, your smartphone is a connected device. Likewise, anything you take, it could be your RO water plant also, which has some kind of connected devices. If it is available, then you can also count them as a connected device. If you are having a kind of automotive switching mechanism at our home, sensing device, which can take care of switching the lights and or your AC automatically, then it's a connected device. Likewise, if you take in 2010, every human being in this world had something like 1.3 devices per person. In 2015, it has become 2, and 2020 it has become 3.96, almost doubled from 2 to 4. And in 2025, now it is estimated every person has 9.27 connected devices. It could be many, starting from your smartphones to cameras to light bulbs, any device that has kind of a connected mechanism, then that is considered as a thing or Internet of Things. So when you say thing stands for such kind of connected devices. Database says that in prediction in 2023, Bosch SI will have 14 billion connected devices of their own. Cisco has predicted 29.3 billion devices by 2023. And yesterday also we talk about this statistics when we dealt the HMI. $1.29 trillion revenues are predicted from IoT solution in 2026 by IDC magazine. So some of the insights are mentioned below. 27 billion projected subscription by 2025. In 2022, Google Home IoT devices market share is at 48%. The average number of connected devices per thousand in 2025 was 10. That's what we mentioned as 9.27. And number of connected devices in 24 is 18.8. So these are a lot of statistics that are available in the Google, so which you can go and see. I think the takeaway is between 2010 and 2025, in the timeline of 15 years, almost it has become 5x from 1.83 to 9.27. That's the key takeaway. So if you want to visualize the Internet of Things, how to do that? So this tree is depicting the entire IoT. You can see here, the roots are sensing. So sensors, like accelerometer, magnetometer, gyroscope, pressure, altimeter, temperature, any kind of sensing device, there should be a sensing mechanism. Then there should be a processing mechanism like MC, MPU, hybrid MCUs, MPUs, and network processor, or whatever it is for processing this data. And connectivity could be several technologies are available. Near field connectivity, NFC, 6LoWPAN, and sub-giga, Zigbee, GPS, right? Bluetooth, BTLE, Wi-Fi, RFID, cellular. So many technologies are today, competing technologies available. Depending on the need, one of them can be employed effectively. So there is a sensing mechanism, there is a data processing mechanism, and there is a connectivity network mechanism. With this, different services and different technologies are being built. And if you see here, the smart factory, when you say you have smart energy, smart parking, smart home, smart grid, smart lighting, smart cars, smart farms, smart tax, and smart health. Likewise, you can see anything with the tag of smart says that it has a IoT device. It's a Internet of Things, and all automation can be affected in the inner ring. What you are seeing now, for example, asset tracking, BLDG automation, right? Remote appliance avoidance, pedestrian navigation, M2M, mission to mission, auto safety, supply chain automation, air quality control. All these devices can be made with the Internet of Things. So by the advent of IoT, all the devices become smart, and with integrating AI, they can become more and more intelligent. So that initially the IoT Internet of Things have been used for monitoring purposes, and slowly they are getting into actuation purpose, which means they can also decide and act automatically. That's the way the world is moving towards. We'll come to, when you say Industry 4.0, as I said, Internet of Things, when you call it a cyber physical system, it applies the entire world. So not only industries, but when you say Industry 4.0, we are more focusing towards factories or industries. So with or without IoT, the golden rule for any business processes, if you see operational or transactional, the benefits are directly proportional to the speed of flow of material and flow of information. There are two things: how fast the material can flow from probably the raw material to finished product, and how integrated the flow of information throughout this process. If the flow of information is fast, as good as the material, then it is a very efficient or effective line. That's the way you can push. So let me repeat. In all business processes, benefits are directly proportional to the speed of flow of material and flow of information. This is the golden rule for any world-class organization. So with this, the introduction, we have just seen what is CPS or Industry 4.0 or Smart Factory and what it constitutes, right? Starting from sensors to some analytics to connectivity network. Then applications are built over that. Once the application is built, it can be called as either smart factory or smart home or smart bin, whatever you call. So many applications it can do. And when it comes to industry, we have to remember, if you want to become a world-class organization, both material and information has to flow together and faster. That's the most important thing. So for understanding IoT, I think the best thing is to understand the application. So let us start with the general application, then move on to industrial application. See here, this is a smart home scenario, interactions in sensing as a service model. I'm not going to explain, I have n number of examples here in the slides, but I'm going to just take one and explain you and leave it to your imagination what can be done similarly for any gadgets or appliances you may have at home. Let us take this fridge. Normally when we have the fridge, probably you know that this is for preserving the temperature. So food products, whatever you want to preserve at a temperature, monitored temperature, the range, whatever you fix, this can be good. Imagine that this fridge is going to become innovative, automatic by inserting no, let it become a smart fridge by way of IoT. How it can happen? That's what we are going to see. Let us imagine that some of the ingredients which you preserve inside this fridge, take a ice cream, for example, or a cheese packet, they have RFID tagged. Okay, let us data. It need not be only RFID. It could be any QR code or whatever it is. Any coding mechanism, if it is attached with that product, just imagine that. Okay, so you have your door sensor reader, you have your RFID reader, and a temperature sensor. All these are embedded in this fridge. Okay, now imagine that it has the capability. You want to always maintain 6 eggs in the fridge, no refrigerator, all the time. Any point of time, you want to have not less than 6 eggs in your this thing. Let us say that you bring a whole packet of 12. You start consuming one by one, and it has become already 6. The moment it has become 6, this information is passed on through a wireless access point to the gentleman now who is the owner of the house. That's one. The same information is also passed on to the cloud platform that supports sensing as a service. Okay. So what the mic is the person, no, or you say that Balaji, I am having a fridge, so let it be Balaji. So I have a fridge which I have defining the rule of, I want to have X number of cheese packets or ice creams or eggs, in my refrigerator. This information is passed on to both the cloud platform through which it has come to me, and I give the decision to go ahead with the purchase. Immediately, this cloud platform checks with the nearest either ice cream manufacturer or supermarket, which is holding this material as stock material. So once it checks, it comes back and say that yes, that it is available. Do you agree for a purchase? When Mike or Balaji says that yes, then it also creates a PO and sent across to ice cream manufacturer. Then the ice cream manufacturer physically transfers this material to the home, right? Because it is already authorized to Mike. And on this transaction happening, Mike or Balaji also will enable a kind of money transaction to the service provider, whether it is ice cream or cheese or egg, whatever it is, it will be done. So at some point of time, even we can have application where the owner can set how many numbers below that it comes. Automatic approval also can be made, so that it will just come and check, and it will inform and take the decision of ordering this material and sending across to the consumer. This is the way the whole things can happen. Okay, so with IoT enabled, the entire refrigerator becomes intelligent. No more you need to. If you take a very conventional way, the first of all you take time even to notice that whether the material is enough or whether you want to purchase it. The purchasing decision, it gets delayed. Number one. By the moment it comes, then you have to make a decision to go to the superstores, then find out whether that material is available. Then you have to make the purchase, and then you have to bring it. But this refrigerator becomes a self-ordering refrigerator. It decides what are all the things it should be there in its this one, and anything that goes down below benchmark level, it automatically triggers a purchase action by keeping the owner informed. So this is just one example, which I wanted to say how things can become very smart with the interaction as sensing as a service model. Okay. Another example. See, I think it has started happening already in India with smart cities concept. Today, Bangalore, for example, if the garbage has to be picked up, previously what happens is, imagine that there is a city which is having 100 roads. Okay, then all these 100 roads have each one garbage bin where everybody puts whatever they don't want, all those things, material they are putting in the garbage is put on that. Sometimes it overflows also because there is no place. Frankly, People come and pour that because it's filled up. It also overflows on the road. This is a kind of very conventional way. And morning time, somebody decides, the corporation, no, or the municipality decides that okay, the garbage truck will go through these 100 roads. So when it goes to the 12th road, probably it get full, no, complete. Then they have to come back and dump them in the recycling plant. Again, they have to go back and start, where they left, and they have to go around. It's a kind of a tedious process, and it's very, physical, and I would say very manual way of handling it. Imagine what's happening in this case now in the picture. The garbage becomes a smart garbage can, okay, with the low cost passive sensors, which triggers the level, whether it is full or half or 25%, all those information can be sent on to your infrastructure with access to energy resource and a long range data communication, which is fitted in the nearby lamppost. And from that information is shared to the cloud platform. Okay. So this is one information. So let us say all these 100 roads with garbage, how much it is filled, that information is available, number one. The same information is shared with, number one, the garbage truck driver, number two, the city council, recycling plant, manufacturing plant, and health and safety authorities. All of them are shared this information. Instead of going sequentially from road 1, 2, 3, 4 to 100, now the decision will be taken in a very different way. Wherever garbage is full, there the garbage truck goes and it takes out. And then when it clears how much it is carrying, the same information where the truck is, all this information also goes to all the stakeholders, starting from city council to recycling plant to health and safety authorities. Once they are dumped, then they go back and again do the same thing. This way, the efforts are reduced seamlessly, and also monitoring is also happen. So I think multiple X of efforts will be reduced. So it is an efficient management system in smart cities supported by sensing as a service. So if you start talking like this on every appliances, you can see here smart thermostats, connected cars, activity tractors. It's a kind of Fitbits. Whatever you have, Ola cars, for example, right? And smart outlets. For children not to put their hand there. So the moment somebody touches, it goes out of power. Those kind of smart outlets, parking sensors. So when you go to cities now, already you know that Bangalore kind of cities are becoming very, very, very traffic congested. So when you go to a mall, you don't know whether you are going to get a parking space. See, when I happen to travel in New York or Chicago, those kind of cities, you are very well informed before entering a parking lot. You are very well informed on which floor, which parking lot is available. So it is possible by connecting the car to the parking lots, sensors, where it is available, location is available, so that you will straight away start going to the parking lot and occupy. So that way you can get and imagine that you are going on a street. Similar way, street side you have to park where the parking lot is available. That will come on your either smartphone or your device, so that you'll spend very less time in identifying the selection of the parking lot. Glucose monitoring, Bluetooth enabled insoles, which can be put inside your shoes, smart garbage cans, which we discussed about, smart even toothbrush, right? See, dental is not taken very seriously in India, but developed countries they talk about it. Your toothbrush can become a connected device, and it can also capture your I would say habits towards how you are brushing and other things. This can be stored or sent across to your dentist also for taking some good decisions on that. So smart weather stations, right? this also helps us to decide. For example, some time back, I saw a startup company in Bangalore, no, who worked on monitoring the air pollution levels. So, example is say, let us say that you have bronchitis or no asthma patient. Um, because of the traffic congestion or air pollution levels, you will be given alarms. Say, let us say you have to go from X to Y. You have three alternate routes. So, by taking this app, you will be in a position to understand what is the best route to take for avoiding air pollution levels, right? So, all these kind of things can be done. Smart gardening, we actually pour a lot of water to the plants which probably may not be needed, so we don't know the right amount. No, everything is time based. If you take industry, maintenance is time based, it is not need based. So by that, no, actually we waste a lot of energy, whether uh, it is a manure, no, what you want to put for the plants, how much has to be put also is important. If you are trying to dump a lot of manures, it is going to be a waste, right? And nowadays, no, it's all chemical, so it is also going to spoil the air. Rather, if you know that how much each plant is requiring, if you are able to measure that, and that much manure also will go into those plants, no, if it can happen like that, and similarly how much water is necessary, that much alone will be given, then it is a great savings that can happen, no. So the biggest thing IoT brings to your thing is, number one, all the data transmission is real time. Number two, suddenly the service, which was kind of random and time based, is becoming need based. What is necessary and when it is needed and where it is needed, there only the service is going to happen. That saves a huge amount of human resources. You see here, when IoT comes into play, there are a lot of people know who I've tried this also. Here is you can go Google it and see Chris dance in the world's most connected point. This information is kind of 5 years old. I don't know if somebody else is doing similar kind of thing now, but he was actually having many things like Google Glass, narrative camera, Blue HR, Pebble Watch. You see whatnot, no, Moto X, Galaxy, it says all things, no. He used to have Fitbits, everything, no, fitted, and a lot of monitoring, no, he was trying to do that. So I think by now, I hope all of you have understood what this IoT is all about. And when industrial situation, you are calling it as either smart factory or industry 4.0, and the application can be limited only by your imagination. Anything you want to improvise by way of real-time data transmission and taking action, you can use IoT as a tool. Okay. With this kind of introduction, let me get into some case studies so that it becomes more interesting now. Depending on the time, I will first handle one case study, and depending on the time, no, I will take more case studies. The necessity of using IoT in a shop floor. Here, the kind of theme or target taken is enhancing quality of decision through IoT by eliminating time lag through concurrent analytics and early decisions. Okay. Whenever you are using a technology, there should be a ROI, return of investments, right? What do you want to do? Imagine the kind of example, what I'm going to, this is a shop floor. This is our company TVS Sensing Solution. It's one of the product lines, what you are seeing on the screen. We call it as electronic component carrier. It's a insert molded component. You'll be seeing in the next slides how the product looks like. Okay. So we want to enhance the quality of decision by incorporating IoT, and also we want to eliminate time lag through concurrent analytics and validation. This is our aim in the test environment. This we did somewhere around 2016-17 range. Okay. I'll explain you how it was done. Imagine there is a product which you are seeing in the screen. It has to go through around 11 machines I think up to M10 it is shown here. Actually, it is 11. You will be seeing in the subsequent slides because EOL testing also is considered as one station. In the first station, there is a stamping press where three-dimensional stamping is happening. Then there is a pre-mold in M2 in a multiplex 85-ton machine. It is happening. Then there is a piercing or trace cutting operation that is happening. Then there is a overmold operation in JSW 160 ton, followed by a truss place assembly. Don't worry about what is the process, right? You take this way. There are 10 processes or 11 processes for making a product. Okay, it has to go through a sequential process from M1 to M11. So this example shows a what I can say a realistic or real-time product, how these machines are connected with the IoT, how these processes and people are connected to IoT, so that we were able to monitor it on a real-time basis and able to take good quality decisions on time. That's the content now what we are going to go through today. Okay, so for all practical purposes, imagine that it is going through X number of processes which are sequential one by one, and when it comes out finally, that goes to the packing. This is the assembly process layout. I hope this is very clear, right? Now, I am going to explain to you what is the kind of IoT infrastructure that was built here. You have to read this from bottom to top. There are 5 phases of IoT. When IoT is deployed in industrial situation, it's called IIoT. So industrial IoT, that is the way IIoT. Okay. Phase 1 is about fitting sensors to each of these machines, and it defines the connectivity between the sensors and machine in the shop floor. Okay, that is the phase 1. Imagine that if there are going to be 10 processes, all the 10 processes have sensors to detect the process that is happening in the particular machine. Okay, that's the way you imagine in a simple way. Phase 2 is the data acquisition. Through these sensors, this all connected to IoT, IO panel. It's called the input-output panel. I will explain you later. This IO panel itself get upgraded to PLCs and later to some light protocol. I'll come to that later. But when we built that first, we did imagine that there are sensors that are fitted in all these 10 processes. Each machine had a sensor that will identify the intended process is completed in that particular. When the process is done, that information is passed on through a IO panel. That's the data acquisition stage, phase 2. Phase 3 is data storage and processing. Okay, and phase 4 is data analytics that is happening. And phase 5, whatever analytics has happened, the output can come to either your mobile or to a shop floor board, right? A kind of big panel, which is available where everybody can see what's happening. So a dashboard, what we call is a dashboard, or it could be the computer of the general manager. So you can connect as many devices as possible, the information. Okay. Let me repeat. The first phase, a physical layer, which is shop floor, where sensors are fitted with machine. The data is transmitted through IO panel to data storage and processing. Then data analytics happens through application. Then the output is shared for the people in a different way. You have to imagine what supervisor wants, that information will go to supervisor. What general manager wants, that information will go to the general manager. What a quality person should have, quality data, that will go to the quality person. So this classification also happens on this way, right? And the relevant data is going to different people for taking relevant decisions. So each person takes a different kind of, I would say, decision. So the classification of data helps them to take the right decision at the right time, and it's around real time. Now we are going to see that physically here. See here. Our first station is a stamping station. As I said, there is a 3D stamping happening. So every machine is fitted with their required sensor. That's what. I hope you are able to see the animation, right? The sensors, infrared sensors are depicted by some animation here. So whenever first the stroke happens, there is every stroke there is a product coming out. So this will be detected. Once this product is good, that will be considered as a okay product. If it is bad, there is some inspection, and that will go to the rejection chute. That's what you are seeing on the red colored one at the bottom. It's a rejection chute. This is one machine. Likewise, you have 10 or 11 machines. Each machine has a intended process. That process has been monitored and measured. That sensor sends the signal, analog signal, to the IO panel. That's what you are seeing here. So IO panel captures the signals from machines. Now you see, from machine, sensors are sensing and sending these analog signals to IO panel. Similarly, you have a ERP system where you can input, for example, there is an order for 100 products. So this process is the making the PO and sending and the material. No, you have to draw material from stores. So all these things will be done through a software which is called ERP. So raw data from there, the PO is generated and it goes to the database server. Then whatever material is processed in the machine, that goes through the IO panel, and analog is considered converted into digital, and it goes to the database server. Similarly, the person, whomever is working in that particular machine, he also intervenes through a HMI, human machine interface. For example, let us say there are critical processes where only qualified operators are allowed, right? Let us say the CE press. Some 5% are out of 100 people, workers, only 5 people are trained in that. By putting either thumb impression or face recognition or by keying in a password, only these qualified people will be allowed to operate the machine. The moment they put their punch in, the machine will recognize that the right person is operating the machine. This information, raw data, also goes to the database server. By this, we are connecting the order, we are connecting the person, we are connecting the machine. All three M's are connected: material, manpower, and machine. All three are connected, and this information is going to the database server. This data is transferred to application, data analytics. The application will have several softwares by which this will transfer. For example, I like to understand what is the level of rejection, or what is the kind of speed efficiency, what is the kind of OEE, availability, quality, and also efficiency. All three put together, that's called OEE. So this information will be calculated instantly during the process, and this information is shared through SMS or through messages. Today, there are many formats available. So you send it to your mobile, it sent to your laptop, it sent to your desktop, or any data visualization panels that is available in the shop floor. So anything you can do. Not only that, let us say that there is a quality rejections or more in some particular machine. This information triggers a tower lamp, which gives a kind of red light or yellow light, depends on the need. And whomever the quality inspector in the bigger shop floor, they will understand that wherever it is called antenna lamp. So wherever this red lamp is going to trigger, so he will approach that particular position quickly to render whatever help is needed. So whatever I explained so far, you can see here, there are 11 processors, 11 machines. There are 11 sensors, 1 or 2 sensors fitted in each machine. The data is transferred as analog signal to IO panel. Simultaneously, ERP transfers raw data. Human machine interface sends the data about the manpower when he is getting into that with either thumb impression or face recognition or password. And all this formatted data goes to data analytics software, and the output is shared, whatever form it is required, to different output devices. Okay, this is the entire IoT model. Physically know how it is connected and how it is working. Hope this is very clear. Now, when we did it in 2000, as I said, 16, 17, that's the way we did it. Later, with the advent of technologies and for troubleshooting, we have started connecting them through master PLCs, replacing the IO panels. Master PLCs are taken and it goes to the edge server, and through that, no, it goes to data analytics, then to the output devices for alerts. So this is the existing setup of gateway. This also is getting upgraded in the third generation by called T-Lite 1.0. So this is a lightweight protocol. So this helps in securing any loss of data from one station to another. So we will not get into technology part today. What is important for us to understand how we can deploy IoT in a shop floor situation. That's what we are saying. What you have to take into your mind is with the machine, the manpower, the material flow, along with information flow, is taken on real time, and it gets into a software where analytics can be done, and immediately we can take the decision also. For example, if you understand that um, 8 hours are there in the one shift, and third hour you are seeing that you are only at 74% of efficiency, you know that something is going wrong. You are losing your efficiency 26% due to many reasons. The analytics will throw you light which machine or which process, really creating a kind of issue. Antenna lamp can really run. It can create noise or kind of light, so that the subject matter expert can immediately approach there without any kind of invite required. So you will be able to go and attend that, so that before the fifth hour, they can put back the efficiency to 90% level or whatever is the prescribed level of OEE. That way we can do it. So the before and after, if you look at before getting into visualization, I want to make it clear. Imagine that there is no IoT. There is a kind of manual operation, which now also I would say 70% of the shop floors in India are kind of manual. So when it happens, one shift completely it is run. There are a lot of data that is taken manually. Quality data is taken, delivery data is taken, now how much output has come, efficiency has come, everything is entered. Then for accumulating this data and doing the analysis, another one shift is needed. Third shift only you come to know that you have lost some efficiency or you have some quality problems. By the time this information goes from desk to desk and go to the right subject matter expert, it could be few days also. There is a possibility. So you are not in a position to take decisions immediately, on a real-time basis. Whereas whatever you are learning from the first shift output, if you are a very best case industry, you will be able to do in the third shift or fourth, next day first shift, you will be able to do the countermeasure. Whereas when once you fit IoT and on real time basis, every hour you are having this information, you will be able to crack these problems then and there itself, so that you will be able to keep up the efficiency or effectiveness level beyond a kind of benchmark level. That's the biggest advantage. That's why I said that quality of decision by the way of connecting all these forums. So visualization screens can be many. I'm not going to delve time. This all you can imagine. For example, operation manager likes to always know what is the OEE, what is the efficiency, what is the machine availability, what are the quality. It can be on minute by minute basis, part by part basis, average production per person, average production per machine, average production per shift, anything and everything, whatever you want to understand, everything can be fed in the analytics, and on real time, it will fetch the information in the dashboard. Okay. The efficiency also can be found out whatever way you want. You can select employee per shift, per day, per machine, plant, run size, whatever way you want to analyze. It's a matter of programming. Once you program it, you'll know which person is working at what efficiency, which machine is working at what efficiency, which process is at what efficiency. Everything you'll know. And you can go right hand side or top. Now you see employee wise, shift wise, day wise, machine wise, plant wise, run side. Imagine that there is an international company which is having 56 plants around the world. If the same product is or similar product is run in these 56 countries, with the advent of IoT and taking the information to cloud, somebody headquarters, sitting in New York or somewhere Geneva, they will be able to understand the same product at what efficiency, at what rate they are being manufactured in all these 56 countries across. That's the power of IoT. The information, real time basis, you will be able to fetch, and you also will be able to benchmark the best. The moment you know that one particular plant is doing better compared to others consistently, you can also learn the best practices can be shared from there to other plants so that they can be upgraded to achieve the same kind of effectiveness. That's the power of IoT. Okay. Last report, downtime, no. All the reasons can be put on that, like want of supply, want of storage, want of IL, want of lunchtime, drum change, want of it's so whatever possible causes can be there for loss of output, that can be put, and you'll be able to analyze and use a kind of either a 80-20 rule. No, you can create a Pareto chart and start knocking one by one so that you can better them out. This for rewards also you can use that, right? For efficiency, if you know that who is doing best, so you can probably recognize them by giving some kind of awards or some compliments. That are all possible, right? Everybody knows in the system, starting from the person who is operating to the supervisor to the manager to the general manager to the board. Everybody knows what's happening, and it's very transparent. So manipulation of data is also completely avoided. Finally, you can get the OEE report. So many things you can do. Rejection entries, QA person can find out. So in the plant layout, imagine here, these are all numbers of the machines. So every machine, the general manager can see on the shop floor, whatever is green is depicted by 80% plus of efficiency. Whatever is lesser, it is all shown in red. Okay. Less than say 50% or 60%, and whatever is above 70% is shown in yellow, right? And ideal machines that are running, they are in a black color. So likewise, if the entire plant has thousands of machines, you will also know which machine is doing what and what is the efficiency indicator. The plant layout view, you can have it. Shift-wise efficiency, you'll be able to see it. And top performance you can see on every shift. Top losses in the past 3 shifts, consistently, is there a loss somewhere that you will be able to find out. Operator-wise rejection quantity you can find out. So many things you can find. All the purpose is to better them. As I know, you have to remember that all these things are done with the purpose of bettering your quality of decision so that you can better improve your total plant. Finally, the conventional system versus IoT. You can see the conventional system manual, it's measured only once in a shift. Manual data collection, manual intervention required for notification and analysis, and implementation takes more time, and compensation not done during the measured window period. Hence, more of postmortem. Whatever data you are doing, if you are trying to, at the end of the shift, if you are finding that it is only at 70% of efficiency, the 30% lost in the first shift cannot be recovered, right? It's gone. Gone is gone. But where with IoT, all the 3 data, availability, quality, and efficiency, are monitored depending on the need, minute by minute or hour by hour, or every half an hour, whatever it is, so that in the next slot of the time, you'll be able to do the countermeasure also. So at the end of the day, you will be able to make up so that imagine a situation where you are likely to get 70% efficiency because of the right you have. Let us say hourly you are measuring, you get 8 chances of countermeasures within a shift, so that your chances are better that you approach 100% rather than 70%. So with this case study, I hope it's very clear. I'll get into, I think we have time, another 10 minutes, I can explain the case study too. This is simply, so imagine a problem case. The products, when it is done, let us say that there is a manual assembly process that's happening. There are 4 or 5 process involved, 5 people are involved. They are doing sequentially. At the end of the day, let us say every 100 numbers they have to pack it. It will become one bag. Then every 10 bags has to be put on a cotton box so that it becomes one box. Okay. So 1,000 products, 10 bags will go in one cotton box. Manual process, what all can happen is after the end of line testing, products are manually counted and stored in bins before moved to FG stores for re-verification. Then packing is done, labeling is done, transferred to FG stores. Lot of non-value-added activities are there, including ensure accuracy by manual counting. Every time you have to count whether 100 products. It can be 99 products or 101 products. It's a possibility. Transportation of material is happening is high. Manual generation of ticket, no, every time from one place to another place when you go, you have to go through a procedure. Motion loss of operators is high and loss of uptime tester due to unmanning. Okay, all these things are happening. So the activity flow is shown here. Total number of activities are 8 activities happening. To visualize this, you are going to see now beforehand how it was handled. Okay, I'm going to show a video. Hope you are able to see it, right? It's a manual process where at the end of the line, you are seeing the testing that is happening on the end of line tester. Once it is done, it is transferred to the FG store. So you can see somebody is coming and giving the material, and this guy is going to put it, and every 100 numbers he has to pack it. So he is also counting physically. Okay. Just to watch the whole process. So he has physically counted. There is a possibility of error happening here. Instead of 100, it could be even 95 or one or two, whatever. Once it is done, he is also pasting a kind of sticker. You can see here. Then these, as I said, no 10 bags have to be put on a bag, and he is doing physically. Okay. This is how it is done on a kind of conventional system. Now I'm going to show the entire process how it got changed now. You can see the new setup after doing kind of study, industrial engineering study. The entire things got connected. You can see now even ergonomics is taken over here. The end of line tester is connected to a weighing scale, then to a QR code printer. Everything is interconnected. Once you make the setup, what happens you see here? The same kind of process when he does is no more counting. You can see that he is seeing it and just putting it inside a plastic bag. This plastic bag sits on a weighing scale. The moment the number of items are good enough, right? Let it be 50 or 100, whatever it should be. Once it is done, what happens you see? You see here, there is a printer, printer comes out with a label. So you don't do anything, you don't count or anything. Automatically it is happening. It is no more shifted to FG stores. It is happening at the end of the line itself. So there is no chance of any error that can happen. You see, counting is replaced by weight based. Then this is put on a box. Okay. Now, this also can be seen by after putting 10 items, you can have another system by which, kind of printer, you see here. Once he does completes, there is a printer that comes out, then he is going to put it. So lot of elimination of manual work is done and error free. Now the customer is guaranteed with when you are doing thousands, millions of millions now every time, there is always a possibility of manual error. The entire thing is completely now error free. That's what is happening. So you can see no activities. Now the activities reduced from 8 to 3. Manual counting is completely eliminated. No re-verification. Material handling is completely eliminated. Auto generation of shipment tickets. No quantity errors in packing, and online inspection reduces inspection time. Okay. So still we have some photographs. Of course, I'm not going to explain much how the AI can be used in the inspection process. Some of the things, no. These are the intelligent systems which are used a single axis robo or soldering station. This is all our line. So machine learning and deep neural networks to help vision system learn, distinguish between objects and even recognize objects. AI is helping to bring vision technology into unprecedented territory. So AI enhances the capabilities of vision system, making them smarter, more flexible, and constantly improving. What you cannot see with the human eye, now with this kind of vision system and artificial intelligence, you can take the decisions much better. Similarly, you can see a welding machine where servo and AI vision systems are used for finding out any weld that is missed out. So I think we have seen the shop floor case studies of IoT, which are very simpler, but of course, it's not as easy as I'm telling. You have to do a proper industrial engineering study to understand where the sensors have to be put, how all the resources involved, whether it is a human being or the machine or the process, how they all can be integrated. Once it is integrated, you have the real-time data and analytics so that the decisions also will be quicker and smarter. That's what is going to happen. What are the key benefits of industrial IoT or IIoT? Eliminate human dependency. You saw already the examples you understood. Proactive decisions, shop floor real-time visibility, quality decision making, high accuracy levels, and resource utilization. These are the key benefits. See, the potential failures could be sensed well before occurrences and initiate preventive maintenance loop to counter such. So it can become very prescriptive, not a post-mortem. And embedded quality data for ready retrieval. Sometimes, no, even you can embed all the quality data inside the product itself by way of some QR code or laser marking or whatever it is, you can do that. And action oriented, it's all benchmarking. As I said, no, you can benchmark across the plants around the world. And it will be definitely a superior customer experience that is going to happen because of this kind of thing. So the customer experience can be enhanced to delay with the higher value proportion. The IoT principle could be applied in the shop floor or automating information flow and improving productivity process. What is the future scope for IoT? What happens to the world with the advent of IoT? There was a fear in the initially that it can become affect jobs. But what has happened is with the automation or even with the AI, it's a matter of only I would say retraining. Instead of one job, it is going to be a more quality job with lesser tiring and more effective. That's the way it is going to be. So you can see it in both ways. Either it affects jobs or also it creates new jobs. Globally, 1/5 of the global workforce will be impacted by adoption of AI and automation. 50% of the companies globally are planning to adopt Industry 4.0. It will have impact on routine manual jobs. Anything that is, that today with the AI, anything that is repetitive, all the banks today, many of the things, you get automated calls and a robot talking to you. So many repetitive things can be replaced by AI. Around 200 million jobs across the globe will become vulnerable in the next year. Already it is happened. So if you track what Elon Musk has told, it's going to have a huge impact in the market. And 25% of the companies globally believe that automation will create new jobs. These are some statistics, like 21 to 30% of new jobs will be created. For example, introduction of computers created millions of jobs than it is impacted. When computer came, same kind of problem came. I think humans will lose the job, but it has created new skill job, no, with computer operators to analysts to program writers to many things. Similar way, IoT and AI, they are all going to bring kind of new set of jobs that are not there before. Jobs that machine complements human labor will be created, such as robo operators. Yesterday we saw that cobots, right? Collaborative robots, which works and enable the operators, troubleshooting, monitoring, robotics, etc. Engineering skills across all disciplines will be needed to design, build, troubleshoot, and maintain Industry 4.0 technologies. But the skills and workforce you require to fulfill your staffing needs will shift from as the new technology is adapted. Okay. So as manufacturers change their business models to take benefit of IoT technologies, IoT-based application can become new business model in manufacturing industries. Considering the application services perspective, it is essential to address privacy, security, and safety. Novel paradigms can be developed systematically in future IoT applications. Artificial intelligence and IoT combined applications are being used in many industries across the globe. The huge research scope is available in this area to seek competitive advantage by augmenting human intelligence. Also, further work can be extended to proactive decision support using artificial intelligence. Internet of Things, only tip of an iceberg. What the change requires in the attitude is adaptability, upskill, and reinvent yourself. That's what is needed. Thank you. I'll stop the presentation here and I invite any questions that you may have so that I can explain further. I'll come on the video now.
Here, if you have any question, you can clear with our resource person. Dear participants, am I audible?
Any questions, please go ahead. No question is a bad question, please.
Dear participants, can unmute yourself. You can unmute yourself and you can ask questions. Clear or doubts to our expert.
Can you make it quick, please?
We hope, sir, that everything, whatever clearly explained in a real-time manner, sir. So they can they understand everything in easiest manner, I think so, sir.
Okay.
Good evening, sir.
Yeah, that is it. It's a participant, sir. They gave
Good evening, sir. Am I audible?
Yes, sir.
Yeah, of course.
Sir, is there any open source software is available for the simulation of this e-mobility, sir? Open
I
source
have no
software
idea.
is available?
Definitely, yeah, it should be available, but it's very dangerous to answer this question whether it can be used or whatever it is, because you have to know how when we are doing this IoT, right, into application, you have to be very careful about what can be used in what, because finally you are responsible for the consequences, right? Consequence management is part of that, which I have not really talked about here because we are talking basics. If you technology side, if you want, probably I can find out and tell you. Just to send the questions to me through the person coordinator. I can share you some data. I'm not supposed to actually give you a kind of prescription on it, but the only thing is the decision on using any open source data depends on the criticality of operation what you are going to do. That you have to take into account.
Okay, sir. Thank you, sir.
Any other questions, sir, from our audience side, participants? Then shall I proceed with the vote of thanks?
Yes.
I'm very happy to provide a vote of thanks for us, sir. Good evening, sir. It's a privilege to have the opportunity to deliver the vote of thanks for this insightful session. On behalf of the management and Department of Electrical and Electronics Engineering, I would like to express our sincere gratitude to Dr. Balaji Venkataman, sir. Sir has given a comprehensive understanding of technological advancements that are transforming the manufacturing industries. And sir explained about more detailed real-time examples about the applications. And one more important thing, sir, as well as gave the information about the data. The data plays a major role in it. That is, in terms of information, right? That things are gives a data visualization. They gave us have given an idea about the data visualization tool, that is, which gave us a more insightful things. And based upon these real-time applications, if the students are able to visit the industries, then they can able to get more knowledge. And as you said, sir, they can able to develop the industrial engineering. They can able to develop the industrial applications where all they can do the industrial automations. If possible, you can give us such a kind of opportunities for our students to develop their projects, sir. If it is permitted, then we will be able to make the things more easier. While we are saying it, it will be very easier for us to do this. Do sir. And last,
Sure.
yes, sir.
Yeah, sure. Please go ahead.
Lastly, a special thank you to our esteemed audience for your active participation and engagement. Having enriched session, sir. This makes an enriched session. Thank you all once again. Thank you, Mr.
Thank you. Take care.
Thank you.
I'm leaving.
Thank you, Mr. Thank you, sir.
Dear sir, madam, the next session will start by 7:30 with Dr. Ravadi madam.
Hello, am my voice audible? Okay.
Yes, ma'am.
Yeah, okay. Please.
Good evening, ma'am.
Good evening, sir. Good evening. I'll be sharing my
Shall we
screen.
start, ma'am?
Yeah. Yes, I will start. Meanwhile, I'll share my screen.
Yes.
There I go.
Good evening, sir, madam.
Okay. My slides are visible. Are my slides visible, sir?
Yes, yes, ma'am.
Okay, perfect. Okay. Yes, sir, we can go ahead.
The 6-day online ATAL FDP Factory Development Program, Day 3, Session 6 is Industrial Cyber Physical System Integration, Advanced Smart Manufacturing for Industry 4.0 by Dr. S. Revati Madam, Assistant Professor, Department of FDP, National Institute of Technology, Puducherry, Karaikal. At this juncture, I would like to invite Mr. John Paul sir, Assistant Professor, Department of FDP, to introduce our resource person.
Happy evening to all. It's my privilege to welcome and introduce our distinguished resource person for today's. It's my privilege to introduce and welcome our distinguished resource person for today's second session, Dr. Ravaji S. Assistant Professor in the Department of Electrical and Electronics Engineering at the National Institute of Technology, Coimbatore. Madam completed PhD in Control Systems from National Institute of Technology, Tiruchirappalli, and have made remarkable contributions in areas such as control systems, cyber physical systems, and soft computing techniques. Her research and academic expertise have earned her recognition not just in India but also internationally, where she has presented her work at renowned global conferences. With a strong passion in teaching and research, Madam have organized and participated in several international workshops and conferences. Her dedication to excellence has been acknowledged through numerous awards and honors, making her a highly respected resource person in her field. Madam have received Young Woman Engineer Award by Institution of Engineers India 2020. We are here fortunate to have her with us today to share her knowledge and insights, and I am confident that her presentation will be enlightening and inspiring. I will hand over the session to ma'am. I welcome you, ma'am.
Thank you for the warm welcome. I see there are 100 plus participants and gathering together for this FTP around 7:30. It's really good to see that people are trying to concentrate on technology and the other side of the day also. I suppose this is the third day of the event of this FTP, and on this lecture we'll be discussing about the industrial cyber physical system integration as a part of smart manufacturing. So we have a couple of case studies also. We have the automobile manufacturing and the process control case study, where we'll witness the industrial cyber physical systems integrations. Maybe I'll start with the lecture, and thereon 1 hour plus 1.5 hours we'll be discussing over this topic. First, let's get back. So let me just take you through this. Maybe this is the third day, but just a review of how it has evolved. Let me take you through this journey, or the fascinating journey of how this manufacturing has evolved over time. And it's an interesting story. Like if you see in the picture, it started in the way back in 1984, where you call it to be the first industrial revolution. So now you this at this era of, or this point of time, the factories were powered by steam engines and water wheels. So that is what it is mentioned over here. So it is factories powered with basic mechanizations available. So it was a huge leap thereon. It was from the hand production and how mechanization had happened. So that is the pointing towards the first era in the way back of 1784. So, and now how we have upgraded ourselves, that is a big leap again. So when it comes to 1870s, we enter into the industry 2.0. So where your mass production and assembly lines revolution were part of the manufacturing industry. So that is the era where you had the standardization, you had the basic electricity, and it is actually, the people call it to be the first or the birth of modern manufacturing. So that is the first big leap that we had as a part of industry revolution. So from 1.0 to 2.0. So the second generation, or the industry 2.0, is fast forwarded into 3.0 in the year 1969, we call it to be. This is when you see where your computers were entering the factory floors, and it's like giving something like a factory is a brain, because you have integrated a computing system. So which is going to, now you have the automation, you have electronics, and the earlier computer control technologies were all involved. So this is what is something like how the brain of the industry has started evolving. Now here where it is really getting exciting is that industry 4.0. This is when the computers are present still. And now we are talking in Industry 4.0, which is starting around the year 2010. The major components or the major entities that we are discussing in this era or bigger leap that had transformed from 3.0 to 4.0 is the cyber physical systems. So that is the topic of discussion today. So we'll be talking about, as relevant to the FDP, so we'll be discussing about the cyber physical system. And apart from it, you have the other components of this era, which are majorly the IoT networks and the smart factories. And taking it further, now we are just moving out how, so in this era it's like how, imagine, we are trying to imagine that how machines can talk to each other, because we are integrating networks, we are having the cyber physical facilities, which is going to enable the machines to talk each other, make their decisions, and optimize the on a larger scale or on a business point of view, optimize the production in real time. So that is the major thing. Now, how we had brain for this industry 3.0, now we are trying to have a nervous system also. Like that is what we are trying to evolve. It's evolving, right? So what is the next industry 5.0 or how it is the beyond, because it started in 2020 and everybody started gathering the or trying to gather what is around 5.0, the era which is beyond 2020. So this is where humans intelligence and the machines work together. So that is the important thing, that you can see the robot and the man working together in a perfect harmony kind of. So we are moving from mass production to mass customization with the presence of cognitive systems. So we are trying to understand what when I tell cognitive systems, that can, which means that that's the systems that can understand the situation and adapt to the human needs. So that is what is industry 5.0, or we are talking about, or it is the smart society. So the key transition elements quickly to look up from 1.0 to 2.0, or from mechanization era to the mass production era. We have the shift in from the individual to standardized production. Then you had the powered, because electricity was available or was put in practice for industry purposes in 2.2. So we have introduction to the powered machinery and development of factory systems had happened. This is the key transition elements from 1.0 to 2.0. So when you see from 2.0 to 3.0, it is the mass production to digital. So that is what we are trying to have this leap or major transition that is happening. So in this transition, we have the key elements to play is the computers. So it is integration of computers, introduction of automation technologies, and some quality control systems. So that was also introduced, are the part of these key transition elements. So when there is a jump from 3.0 to 4.2, it is now from digital era to industry 4.0 era. So where your systems are all connected. You have smart technologies. When I tell smart, it is IoT in picture. You have decision systems, so which is data driven decision making. All are they playing the key or the major components. So next, or what is future, which had started in the year 2020, it is from 4.0 to smart society. So now you have AI driven processes, sustainable practices, and advanced human machine interaction, because all are going to, both the human and the machines are going to work on the same floor in harmony. That is what. So advanced machine, human machine interaction is all possible. So this is the evolution, or how it has transformed from 1.0, from the basic fundamental traditional era to towards the future, how it is transforming. Now let's examine, okay, the foundation of the manufacturing systems before 1970s, so that we'll be able to understand how we have come and why cyber physical systems are present in such an dramatic advancement. So the first thing is that the foundation, when you talk about it, is pre-1970s. So you have the manual assembly lines and the fixed automation. So before 1970s, it is all manual assembly lines and the fixed automation. So the manufacturing was primarily very much linear, fixed assembly lines where workers perform a repetitive task, we can call it to be. So repetitive tasks at the same, it was like stationarily people would do the same task repetitively. So that is called fixed automation. And you have the human operated machinery and tools. So this is all where the basic things that had laid the foundation for the manufacturing system. Then the documentation, if you see, you have to go with paper-based documentation and planning. So all production, your planning, scheduling, tracking, all were done manually. So you can see the how hefty things would have been and how trivial things would have been when it was paper-based documentation and planning. It was this was a major problem because this has led to some delayed information flow, some difficulties in tracking the real-time changes, and you have to imagine the volume of the paper that has been required or has to be maintained. So when you see the storage and retrieval were very much challenging when it was paper-based documentation and planning were there. So, and obviously you will have the risk of data loss or any damage because you cannot maintain it for over years. You cannot do it. So that was the major, it was all laid foundation. Traditionally, these are all followed. And you had limited quality control. So quality control mechanism were only limited because human intervention was only, human interventions only were there in quality control mechanisms. So it's like inspector would check the products at the end of the line, and after the defects had already been because it would have gone through multiple sections of the assembly line, and only towards the end of the end point people would be checking for its quality. So it is like towards the end of the defect where it had crossed already multiple stages or units. So that was the limited quality control mechanism that we call it to be. And for example, if you see the old videos where you can see even Charlie Chaplin working on the same task or screwing it up repetitively. No, that is how you can see, say for example, the early Ford assembly lines where fixed conveyor systems were there. So the parts would be moving across in the conveyor system, and persons or the workers would be there doing this task of screwing up the nuts or the bolts, standing in same position, doing for millions of products that goes along. So there is, when you see there, their skill development is just very much oriented. Just they have to do that single task repetitively over the other. There's no skill development was there. So these are the, anyways, these are the foundation before 1970s, which were the traditional manufacturing systems were there. So when you look for the key characteristic, it is the sequential production flow, fixed production schedules and limited flexibility, manual quality inspection, and isolated production cells. So these are all when you look overall, when you look into the characteristics of the traditional manufacturing system. So now let's get into the, or let's explore what has changed when you go or when you integrate digital technologies. Now, how this digital technologies have transformed manufacturing from the period of 1970s to 1990s, because that is the place where your digital computers were introduced or put in the, or deployed in the factory floors. So this is the period where you had the digital technologies integration happening. So when you see the prime thing or the in the early automation, what are the prime things that were integrated as a part of digital technologies is that the first thing is that you had introduction of the programmable logic controllers, your basic PLCs that you see. It started its existence in 1970s onwards. So the first PLC appeared in manufacture, say for instance, in 1960s itself, and it came widespread in a variety of manufacturing sectors in the year 1970s. So we call this period of 1970 to 1990s as the early automation period. So the basic feature when programmable logic controllers were there, which means that it had replaced the relay-based control systems. So already relay-based control system has been replaced with the programmable logic control. So that is the point of emphasis here. And when there is something like programmable logic controllers, now you have the you're trying to, or you're facilitating flexible automation. Okay, so that is the major outbreak there. So you had programmable logic controllers which enabled flexible automation. So the impact is very important because PLC revolutionized the control systems. So in many aspects. So say for instance, it had improved troubleshooting. That is one important aspect that one has to talk about. So it was all program, you know where the logic has gone wrong. So it was very much facilitating in troubleshooting because it was not so possible in the earlier relay-based control systems. So this was important breakthrough in the part of automation. Next thing is that computer-aided design and manufacturing, your CAD CAMs. So they transformed the product development and manufacturing. So that is the major outbreak over there. So this breakthrough has impacted in the way like it has reduced the time for design to the production, and in the ways of it greatly improved the quality of the products. So when your computers were deployed for design and manufacturing, yes, the productivity or the quality of the product has improved drastically. So that is the second breakthrough. And third is that you have basic robotics in assembly lines. We have deployed basic. When I recollected, we have the first industrial robot introduced in the automotive manufacturing sector only. So I suppose Dr. Balaji, who had been the previous resource person, would have discussed greatly about industry 4.0 trends in a better way, because it was early, it was started in the automotive manufacturing sectors. So, and now I'll be discussing in my later slides how in automotive sector, how the industry 4.0 scenario in the factory floor has been all visually you can be able to appreciate it. Next is your electronic quality control system. So electronic quality control. So earlier it was physically inspection were made by persons over there. So now when this electronic quality control systems, what do I mean is that you have some automated inspection systems, some basic digital measurement tools were there, some data collection capabilities were there. So in all together, put together, now you have something called as electronic quality control systems. So which were more consistent, okay, more consistent in quality checks, and it was like it was working in a faster way in order to detect the issues, and at the other point, since the digital measurement tools were available as a part of this quality control systems, now you have better documentation of the quality data. So all these were very much easier. So the first, as I told you, the first robotic welding system was deployed in Toyota, who were pioneering the use of this robotic welding system in the car manufacturing sector. So that is the part of early automation, and these are the basic digital evolutions that have been taking up its position in the manufacturing sector or the industries, basically. Next, we'll be just starting about this, or we'll have a brief overview of this industry 4.0. So generally, what if you want to define industry 4.0, it is represents industry 4.0 represents the convergence of cyber physical systems, IoT, and intelligent automation in manufacturing, enabling smart factories characterized by self-optimization, self-configuration, and artificial intelligence. So this is the basic one-line definition they give for Industry 4.0. When you see, there are four main pillars which are very much holding this industry 4.0. So first is the interconnection. So machine to machine communication, human to machine interaction, and seamless data exchange. So these are all possible. So first point to understand is the interconnectivity. The next is information transparency. So you have digital twin technology. So we'll be discussing what is this digital twin. Okay. So digital twin technology, real-time data collection, and contextualized information. So that is information oriented to a context. Okay, you're trying to collect data for quality control. So the best products which are certified those databases are collected. So you have all these possible when you have information transparency. So that is all possible with industry in the era. It has been a major pillar in industry 4.0. Next is the technical assistance. So the decision and support systems, the predictive maintenance, and the visual assistant tools. So these are the key components for this technical assistance, which is the third pillar. The next is the decentralized decisions that it is making. So because industry 4.2 is cyber physical systems, IoT, and the machine learning techniques and the informed decision makings. So as a part of this, now you have decentralized decision making where it has got or a sector or a machine has got autonomy over making decisions. So that is autonomous systems. You have AI driven optimization technologies deployed. You have under this agenda of decentralized decisions, now you have smart resource allocation. Okay, all these are all standing for pillars for this industry 4.0. And when you see under this roof of a smart factory in the era of industry 4.0, you have collectively deploying all these components or elements together. Now you have the great picture, which is like the business impact. We are trying to understand the business impacts of the industry 4.0. This is a small database that we have collected from through survey. It is 84% of productivity increase it has brought. Okay, and 60% of reduction in machine downtime. And we have seen 50% of decrease in quality cost and 40% reduction in the maintenance cost because of all the collective technologies working together as part of industry 4.0. So if you see that it is a comprehensively, you can see it is an digital ecosystem. Okay, where your physical manufacturing systems, okay, be it a sensor or a machine or a robot, is able to get integrated with this digital technologies, and thereby it is trying to bring out all these benefits in the operation as a part of operation improvement, we can call. So you have the you can see the various components, like you have industrial IoT control system, you have smart sensors, you have web mobile HMI systems. So you can see all other interconnecting elements. You have big data analytic components all together are interconnected around the smart factory. So around this smart factory core, and it is trying to demonstrate how holistically the nature of 4.0 implementation has performed through this statistics. So now let's understand what is telling the 4.0 transmission. So from digital technologies has entered into the factory floor, and how this has evolved further in smart manufacturing revolution. So now let's explore the industry 4.0 that is representing a fundamental shift in the manufacturing sector. Now, when I tell this smart revolution, smart manufacturing revolution, the first thing that pictures out in the core, in the schematic that I've shown earlier, is that first component is your IoT, so which is Internet of Things integration. So IoT connects physical devices and machineries to the digital network. So that is one thing. Okay. So when you see for this IoT, the key feature is that your your sensors are going to become smart. So now your smart sensor throughput production is possible. Okay. Next is you can with this IoT getting integrated, you are able to read the real-time data, or you will be able to have real-time data collection possible remotely. Next, you have possibilities of facilitating device to device communication. Next is the network connectivity. I show in the later part of the structure how the architecture of the industry 4.0 has been with an example. So in that I'll be discussing like how this network interconnectivity is very important. So the next big thing is that big data analytics. So if you see the functionality of this big data analytics, the first is, as I told you here, it is real-time data collection. So in this phase, it is real-time data processing. And it has played a major role in quality checks also, because some pattern recognition, predictive analysis, performance optimization, if you see all these factors are a kind of consequence of this big data analytics capabilities. So you with this big data analytics being performed in the factory floor, you can have data driven decision making, you have process optimization, quality improvements, quality checks, cost reduction, everything is being brought into picture. Next is the cloud computing infrastructure. So cloud computing is, you're trying to you've collected the data, you've done some analytics over it, and now it is the point of data storage and processing. So this is the data storage and processing point. So you are trying to trying to provide a remote access. So when it comes as cloud computing, you're sitting elsewhere, not in the premise of your factory, but you're sitting elsewhere, and you're trying to access the data. So that functionality is being built. So remote access capabilities is one feature that has been enabled through this cloud computing infrastructure. And something now we are again going ahead is software as service. So you are having the data, now you are when you are having the data remotely available, now you are trying to provide a software as a service remotely also. So that is another feature you can call as a part of smart revolution. And next point is the artificial intelligence and machine learning, which is very important, because the application is very vast for when applying or deploying AI and machine learning. So you have automated quality control, you have process optimization, predictive maintenance, as I told you, production planning, everything. Wherever you see, you have artificial intelligence and machine learning playing a great role. Okay, human intervention or expert intervention has been now the paradigm shift is like now AI is doing all the job. Yes. So one example, I'll just show you how intelligent your production lines are. One of the here the quoted example is BMWs, but I'll show you a Tesla visualization where you can appreciate the smart manufacturing, how it has been deployed in the factories. So, so when it comes to these are the technology, these are the revolution that has taken up in the industry 4.0 transformation, and very impressive key technologies we call to be like, first one is the advanced robotics and automation. So nowadays people are not calling to be robots, now they are collaborative robots, so which means like cobots. So you have cobots, you have intelligent automation, you have flexible manufacturing, everything possible with this advanced robotics and automation feature. So that is the first technology, which is very impressive. The next is digital twin. So what is this digital twin technology is that you're trying to virtually replicate a physical asset or a physical process. So you're trying to mimic it, or you're trying to virtually make a replica of the asset or the process. So that is the basic concept behind the digital twin technology. So the application is that when you see when it comes to application in the industry, it becomes like you go for basic process simulation, your performance optimization, predictive maintenance, and basic testing. All that you do with this technology, which is called to be the digital twin technology. Next is additive manufacturing. So because everybody now are with this word, magical word, additive manufacturing. So where what comes into mind when you talk about additive manufacturing is your 3D printing technologies. So 3D printing, rapid prototyping, custom production. Okay, what is required? So that is are the key technologies around additive manufacturing. Now when such 3D printing technologies or your custom production is all possible, then you're trying to have a design flexibility, and you're trying to have a rapid production, which means faster product development is all facilitated. So that is another key technology that is playing in the era of 4.0. Next is the integration of smart sensors and the actuators. So the everything becoming smart is that you're trying to have a real-time access or real-time monitoring over the process of the production line. So that is the where you can have continuous data collection. You have continuous quality monitoring. Everything is possible when you have real-time monitoring systems. So the basic feature is like continuous data collection and monitoring, and monitoring for quality, for that is the matter. So for you, through the smart sensors and the real-time monitoring, so this combinedly, when it go hand in hand, you have immediate response, you have improved quality, you have you will be trying to greatly reduce the downtime of the machine. Okay, because everything is real-time monitored and quality checked. So these are the this, if you see the in this 4.0 transformation in the transformation, you can see the convergence of you can see all the digital and the physical technologies are getting more intelligent, more connected manufacturing systems. So now let's see how specifically impact the cyber physical systems in the modern industry. Now, it is understood that your cyber physical systems play a vital role in the modern industry by trying to create an seamless integration between your physical and the digital entities. So first is that is the major point. Okay, role of cyber physical. So it is basically the integration or the connection that you trying to make up. So CPS or your cyber physical system serves as a bridge between physical and your digital manufacturing operations, or the control systems for that matter. So they are trying to bridge the gap between the physical and the digital entities. So you have sensors, actuators, part of this physical integration, and you have your digital interfaces for data processing. You have communication networks for connectivity. You have the basic control algorithms for decision making. All you're trying to integrate it. So that is the first role of cyber physical systems in the modern industry. Next is real-time data processing. As a part of this, as mentioned earlier, continuous data collection from the production lines, and you're trying to make that instant processing. Okay, because the data is processed in real time. So instant data processing of the operation data, and you're going for real-time analysis, and we are trying to get the real-time response. So that is the key feature, or that is the essence of CPS getting into the modern industry. So you will have a greater benefit when you're trying to have this real-time data processing. So you'll have immediate product problem, any problem detection or quick decision making and sometimes you can have some proactive system adjustments also. So this is when your data are going to fluctuate in this way. So you'll be able to get those data in real time and have proactive decisions to be made. So that is one interesting fact as a part of the CPS that has been facilitating in the modern industry. Next is automated decisions. So we have very much. I'll discuss you the very basic application in the automotive sector in my further slides. But AI-powered decision systems has played a very role in all walks of the factory floors. So that is very important. AI-powered decision making, automated decision making. You have a lot of learning algorithms, adaptive control mechanisms, all playing a great role in automated decision making. And if you see, as the impact of it, you have the reduced human interventions, where you call consistent, proactive decisions again, we can is possible. So this is the part of automated decision making. Next, you have the predictive maintenance capability. So you have sensor-based monitoring, performance trend analysis. You have possibilities of failure prediction models. So when you consider what do you call predictive maintenance capabilities, there is a large scope of researchers to pick up topics, because condition monitoring is very much essential. You have multiple, you can club these artificial intelligence and the predictive maintenance capabilities that has to be harnessed very well, because as a researcher, if you see, we work on condition monitoring. We have a lot of scope with respect to failure prediction models development. So and root cause analysis, everything, causality, we call it to be the causality mapping. So there are a lot of things also. So though I'm mentioning all the importance of CPS in the modern industry, but anybody, be it a mechanical researcher or an electrical researcher who are involved in automation, they have a very good scope on all the aspects of the CPS. That is what I want to bring it up over here. So when you look into the impact wise, so you have flexible manufacturing systems, dynamic production scheduling, real-time quality control, and adaptive process control and end-to-end traceability. So this is the impact that it has brought in production. So very quickly, I will discuss with the next few slides. So this is the illustration that is depicting the transition between the traditional to CPS. So you can see how it has been emerging when you're into the domain of CPS based manufacturing. So it becomes generally you are having self-optimized production, cloud or edge based. Cloud we have talked about. Edge is even more interesting because you are not transmitting the data over cloud. So your data processing or your decision making, everything is made at the edge level itself, which means at the point of measurement itself, your processing, your decision making, everything is happening. So that is also an interesting area to explore, which is edge computing. Very much essential when we talk about the modern industry. Next is predictive AI. So the key features are being mentioned. So these are the basic transition that has been it has taken. Okay, so this is like how the key transmission elements have gone through itself. So you have two entities over here, two critical elements. One is that physical to digital integration, and we have to talk about digital to physical integration also. So when I mean digital to, when I mean this physical to digital integration, this is something like capture the real world data and create some digital records. And while I talk about digital to physical integration, I mean that I take digital information and use it for, or I use it to drive some physical manufacturing process. So across like that, under that connectivity, we are just telling that you have sensor networks, throughout the production line. You have real-time data collection. Now you have process twins, automated control systems. You have smart quality management. Everything is all up when it comes to physical to digital integration, and it comes to digital to physical integration. You use the digital data to improve your adaptive production lines. You are trying to automate your material flow, connecting your tools. All these becomes a consequence of digital to physical integration. This is the key transformation. And as I told you, this is a quick visualization of the Mercedes-Benz 56 factory floor. I'll just quickly. So this is the quick video of the Mercedes-Benz, the factory floor. So you can see how it has pushed its boundaries, and how in the possible modern production lines, all you can see all the inventory numbers of all the components has been tracked. It has been recorded, how it has been quality checked. Everything is digitized. Everything, everybody is interconnected over. So this is what we are calling, or we are trying to have as a part of modern factories. So this is one example. So we have in along we have Tesla. If you consider the automotive industry, then you have Tesla, you have BMW. Everybody working on this, or everybody is trying to push their boundaries to just tell, or to show what is possible with this modern production environment. So that is the basic thing. So you would have visualized it in this video. So quickly we just understand. Okay, when we talk about manufacturing sectors, so two benefits we have to consider. One is that the manufacturing benefits, and the other one is the business benefits. Let's start with the manufacturing benefits. So now you've just understood how your CPS has been remarkably integrated in the production line. Just in the you would have witnessed in the previous video. Now imagine how your manufacturing system can now kind of bend and do flex with your needs. So what do I need? That can be imagined of, that can be done as well. So that is first thing, increased flexibility. So you can what is the customer needs, or how the manufacturing sectors has to be altered. It is very much flexible. That is what is to be emphasized. So now it's like having a good game. Now say for instance, if you are having a good athlete in the ground, now understanding the scenario, how he has to pick up the speed, understanding the gaming situation, how he has to perform. So that is now requirement of all factories now. So first is that how is your flexibility levels when it comes to manufacturing. So that is the first point. Next is higher quality. We are seeing higher quality products because these systems can catch issues before they become problems. So instead of one person or one expert having thousands of quality inspectors working across 24/7, who never getting tired. So what is in that case you need some AI based quality checks, or robotics based quality checks has to be available. So that is the impact in the industry 4.0. You have higher quality products available. So because here you have the role of AI, you have role of pattern recognition, all working together in the factory floor to give or to promise the quality products being delivered. Next is the reduced downtime. So reduced downtime is particularly very much exciting because it's like a car having getting having that, you can tell that it needs maintenance before it breaks down. Okay, that is so it is not so that kind of reduced downtime your elements of industry 4.0 are going to give you. So that is reduced downtime. The next is that you have better resource utilization. So now your factories can optimize everything, right from your energy to your material consumption, and everything we can do it. So that is the part of material resource utilization. Next is enhanced traceability. If you see that in the previous video that I played, you will be able to have the inventory number of each component that is placed in the every part that is being placed as a component in the car. So that is the you can understand what is the date of manufacturing of that inventory or that component. So that is the enhanced traceability capability that manufacturing sectors look for. So that are the manufacturing benefits when it comes to CPF getting into the industry. So next is the business benefits. So that's really interesting because when you talk about industry, the other end is business. Okay, business benefits. That is very important to talk also. So you see faster time to market. So when you put CPS, or when you have the role of CPS into the industry, then you have all possibilities of getting faster products to the market. So that is faster to time to market. Next, you have reduced operational cost. Reduced operational cost is like something like you just imagine how you are trying to upgrade from an old phone with an inefficient smart factory. So that is not possible, right? That is not that is not go hand in hand. So if you are going to go for some enhancement, or when you are trying to upgrade something, then you should have operation cost to be reduced. So because every day you see you have everyday enhancements only looking up day by day. So in that, the controversy is that you should have to reduce the operation cost also. The next is the improved quality metrics. This is a little interesting when I talk about the quality metrics, because you are you're trying to sell a product, so a better customer satisfaction comes when you that feeling comes, or that satisfaction comes when you are selling a better quality product only. So that is the basic agenda. As a part of business, you should have products to be customer satisfied. So that customer satisfaction would be coming across when you are trying to have quality products to be sold. The next is sustainable. So everybody is interested towards this last step, because when it goes or when we are trying to move from era 4.0 to 5.0, the one of the important future manufacturing sectors main key is sustainable operations. Where we see automotive plants are now just efficient in producing, but also how environmentally they are responsible. So that is also a part of business nowadays. So these are the impact of manufacturing and the business benefits. Now quickly I lay down the CPS foundations. So let's talk about the CPS foundation. When you look into this, the first thing is that I tell you, it's computation, networking, and physical process getting together. So that is what we just understood, the CPS. So it is typically very equivalent. Say for example, you are in an orchestra, and the instruments that you play over there are something like your machines that is in the factory, and the musicians that who are playing are the computers over here, or the computing platforms, and the conductor is the network, that is your network. So all the three components in an orchestra has to work in harmony. So that is what integration of computation, networking, and physical processes is actual meaning, which means your physical process is nothing but your body, and your computation is your brain, and your networking is your neural system. So if all work together, then it's perfect. Okay, so that is the integration of the entities when it comes to cyber physical systems. So the core concepts are three main. One is real-time operation, intelligence, and the connectivity. So when it comes to real-time operation, it is like something happens on the factory floor, there is no time for delay. The system has to react immediately in a right way. So that is that is first core thing that it has to address. So real time operation, continuous monitoring, immediate response capability, and time critical operations. That is what. Next core component is your intelligence. If you see that it is imagine having a manufacturing system that not only going no more it is just following the instructions, but actually it is going to learn and get smarter, just adapting to the environment over time. So that is very simple. So data driven decision making, adaptive behavior, and learning capabilities, these are part of this intelligence concept. The next is connectivity. It's something like a glue that is going to stick all together. So it's like something like there is some universal language, and you're trying to connect all your systems, speak through that language. So that is connectivity is all which is going to gel your physical, your cyber components together. That is your connectivity, which is playing an important role. So that is through seamless communication, network integration, and information sharing. So all these are the important things when we have to discuss when you talk about the cyber physical systems. Let's understand the core components in much more detailed way. As I told, cyber, physical, and integration layer are the three major entities, components, or the three main layers that are eventually playing a great role. So this when you look into the first layer, or the physical systems, You can see this is going to consist of three components. The first is the sensors, which includes your any sensors, like typically your temperature sensor, your pressure sensor, your flow meters, basically all the sensors that are relative to your industry environment. Next is your actuators. So your actuators in an industry environment can be an electric motor, or it can be an hydraulic system, or it can be a pneumatic cylinder. So be it anything. So they are part of the physical system. The next third component are the controllers. So basically you have your PLCs, your DCS, we have the industrial PCs, dedicated industrial PCs, your CNC controllers, safety controllers, all these which manage and coordinate the physical operations. So that you call to be the controllers. So all these come under these components come under the category of physical systems. The next is your cyber systems. So this layer represents the digital and the computational aspects of the systems. So it includes your computing platform, like your edge devices, industrial servers, cloud infrastructures. The next is your software. Next is your software systems. So which is going to comprise your software systems, like your SCADA that we use in the industries, SCADA systems. You have the manufacturing execution system that we call it to be the MES. You have the ERPs, which is enterprise level resource planning. So energy management systems. So these are the software systems that becomes as under the roof of cyber systems, and be it the analytic engines, because that also comes under the category of cyber systems. So you have real-time analytics, you have predictive maintenance engines, you have quality control systems, process optimization models. Everything comes under the roof of cyber systems. The next is the integration layer. So this integration layer serves as a crucial bridge between your physical and your cyber systems. So in this layer, you have the communication protocols like your OPC UA, your MQTT, your Modbus protocols, your Profinet, all these communication protocols that we use in the industries, all comes under the category of the industry integration layer. Next, you have the middle-based solutions like your message brokers, your ESBs, API gateways, all comes under the category of integration layers. Next, you have the API components. So your API components, like when you see you have the WebSocket API, you have the legacy system adapters. You might have an older version of the system and a modern factory. So you should have a legacy adapter to it. So you have a legacy system adapter. So all these would comprise the integration layer, which is going to interconnect your physical and the cyber entities. So this is where I just want to show you the difference. So how is your hierarchical and your industry 4.0 architectures? So we have the hierarchical model. Is for that you have the ISA 95 architecture, and you have the distinct industry 4.0 architecture as well. So this traditional excuse me. So this traditional ISA model or the architecture is when you see it is pyramid shape or hierarchical shape, hierarchical. So which means that we have distinct layers starting from your physical process at the bottom level, and through your sensing and actuation. Next, you have your monitoring supervisory control, and you have the manufacturing operations. Then you have your ERPs, that is your business planning. So all these are the hierarchy that is from the bottom down approach. So this is the basic or the conventional top down approach where the information flow happens. So it is primarily vertically through the defined channels. That is what the data exchange happens in this hierarchy, and this indicate the what you see is that very indicative that how your structured data exchanges are made in this architecture. So this is the hierarchical architecture. But when it comes to industry 4.0 with the with the capabilities of cyber physical systems being integrated, you can see how you can contrast it. So what you see on the right side over here is the industry 4.0 architecture, which is an interconnected mesh network. So you can see, you can have multiple nodes that are connected through the various pathways. Okay, so this modern approach is going to enable direct communication between different components. Say for instance, these are different components falling under the different hierarchical levels that are just represented over here. So, but now you can see that this mesh is going to allow more flexible and dynamic data exchange to happen between different parts of the manufacturing system. So this is being eliminated. This hierarchical architecture is now getting eliminated, and you have direct communication being possible. So, so what are the key characteristics of this Industry 4.0 architecture is that is being defined based on the data flow attributes and the data characteristic. So first thing is that real-time communication. You have a bidirectional data exchange. Secure. So when I talk about cyber physical systems, then obviously we have cyber security is also involved. So secure transmission is the next thing. You can scale up the bandwidth. Next, you have fault tolerance capabilities as part of data flow attributes. The key characteristics, when you see, you have the modularity, you have scalability, interoperability, because you have multiple vendors, but so that operability are possible when you have this kind of data being exchanged. So that is the interoperability and real-time capability, service orientation. So these are the possibilities it should have. The key characteristic of your data when you are trying to put into this architecture, which is Industry 4.0 architecture. So, in a nutshell, if I had to brief, this is going to enable more direct communication paths, and it is going to be more faster response times would be there, and you can have a greater resilience because you have multiple pathways for data transmission to happen. So which means that multiple connection routes are just giving more system resilience. That is very important, which we have to highlight. So that is the difference in the architecture of the hierarchical and the meshed communication. So now quickly, what is this architecture? When you have cyber physical systems into picture. So we have generally in research they call it to be the 5C architecture. So this 5C is nothing but you have connection, conversion, cyber cognition, and configure. So all these together working under different layers are the 5C architecture. So this 5C design provides you step-by-step guidance for developing and deploying the CPS for manufacturing applications. So the 5C design, if you see, it is very much sequential workflow, because how to make CPS from initial data acquisition, okay, from that level to analysis level, creating a final value is being understood. So this is telling you, this is just a brief guidelines or how one should have go about in designing a step-by-step in developing or deploying the CPS into the factory floor. So this is given by this guidelines. So the first is the smart connections that you have. So first step in developing an cyber physical system based application is to obtain accurate and reliable data. So that is the first thing from the multiple points or from multiple points of the process or the production line. So that is the first important point. So next is that in data to information conversion. Okay, that is the point of note. So the first you will start with data acquisition. Next you have to convert into an information. So this meaningful information must be deducted from the raw data that you collect. So at present there are several tools and methodologies that are available for conversion from data to information. Whatever I mentioned here are the application of each. When you go with data acquisition, you can perform condition based monitoring. When you are converting into an information data, then you can have prognostic or health management. Okay, so each progress that you make in integrating the cyber physical system, you will be able to have the appropriate functionality added up to your industrial application. So the third part is your cyber. So this is the practical level which acts as the center of information in the design, because the cyber is the component now you're taking. So now your data has been acquired, it is being converted in information, and now you are trying to transform it. This information is driven from one machine to another machine through the connectivity that you create. So you have the peer-to-peer monitoring, or you have the possibilities of networking your machines are possible here. So this is what you see. How your the robot arm, multiple robotos arms are connecting in a collaborative environment. So that is the practical level that you have to understand. Next is the cognition. So at this stage of CPS deployment, you will have a thorough knowledge of the system being monitored, and now you have a right presentation of the experience that is obtained from the expert users to support the decision making. Okay, so now you're trying to build up a support system. So that is, you are trying to use the expertise knowledge over the information, and you're trying to design a support system. So that is decision support system with use of your AI technologies or machine learning technologies, you do it. So now which task has to be prioritized, so that decision can be made. So because you have the comparative information coming up from individual machine status, so now everything is available. Now your decisions or your guidelines will be very much important when you're trying to optimize your priority task, or mere optimization of the maintenance process. Everything can be made. So this is appropriate infograph that is or the presentation that we give for the knowledge about the information that has been gathered. Nowadays everything is available for the user to entirely have a visualization of it. Next is the configuration. So this is the or this level is called to be the feedback that we get it from the cyberspace to the physical space, and that is so you have the supervisory control. So based on it, you can have self-adjusting mechanisms. So you can have the required actions to be performed. So that is the supervisory control that you have. So this stage acts as an resilient control systems, because you will be trying to apply the corrective or the preventive decisions that you have taken from the previous will have been will be something like whatever is made at this level is monitored over here. So you would have made some your machine through this decision support system should have made some decision, and now you're just having a monitoring or supervisory control over this, and now you'll be able to have a resilient system, residual control system, like because already a decision has been taken. Now you have a supervisory control to monitor it, and say for instance you can decide upon actions to avoid all that statements to be made over here. So this is the stage or step-by-step guidance that we will have in developing the CPS for the manufacturing applications. As mentioned earlier, these are the key components that will be widespread across this architecture at various levels. So one of the application, a reference model that is derived through this 5C architecture is this RAMI model, which is the reference architecture model for Industry 4.0. So what you see here is presenting a comprehensive layered architecture framework. It's a basic framework which is very much for the modern industry or the industrial systems they call it to be. So there are 6 key architectures. So there are 6 key architectural layers working together. So at the top you have the business layer. So we see the manufacturing operations. You have the real-time monitoring, visualization, all happening. Your applications, user interface applications, everything happening at this layer. The next is your next beyond this you have the functional layer. So this will be comprising of the data analytics tools, your system definitions, your risk assessment, and the decision making tasks that you have to do. So that comes under the category of functional layer. So next step would be information layer. So this handles both your batch and stream processing data that is available. That is going to be handled by this information layer, and some edge based solution, because we are talking about the edge based solution. So such edge based solution databases are available over here. So storage of the data of the edge analytics data has been fragmented over here, and no SQL database and time series database, everything would be coming as a part of the information. Next is the communication layer. Communication layer, which is going to manage your IoT gateway, your message queue system, that is your event broker, your legacy data uplifting. Everything happens over here in the communication layer. Next is the integration layer. So in the integration layer, as I told, which is going to connect your physical sensors in the machines and your HMIs, your legacy systems like your SCADA, everything is going to get integrated in this layer. So that is your integration layer. And next, below that, or the ground layer, is going to be your asset layer, which is going to represent the physical components, that is your machine operator and other users. You have the production line machines. So everything that is comes beyond will be considered as asset. So that is the 6 level of layers that are coming as the part of this RAMI, that is your reference architecture model for Industry 4.0. So this architecture provides a structured approach of implementing the Industry 4.0 concepts. Whatever you see here for seamless integration right from the factory floor to the business level. So this is one reference model that has been followed, and this architecture is being utilized in multiple organizations. So just a depiction of it. So now we'll quickly get the implementation examples, which comes to the part as automotive and the process industries. Maybe I'll just go with this automotive industries, manufacturing sector. So when it comes to the automotive factory, the same features, because you would have witnessed it in the previous video. You have the factory that is where everything is connected. You can have the assembly lines to the quality control. Everything is getting automated or connected. You have smart assembly lines that can adapt or we call it to be reconfiguring itself. Okay, adapt to itself. So next you have the automatic quality control. That is something like catching the issues before they happen, before they become a huge problems. We are trying to catch it up. So that is the automated quality control. Next you have the real-time monitoring and control. That gives you the instant insights. That is what monitoring, processing, analytics, everything happens in real time. Next is integrated logistics systems, which is your, exactly where everything is and where it needs to go. So that is what you see. What is the next item that has to be getting into the car system. So that tells you or that gives you a tracking of the logistics that is in the supply chain. So that is integrated logistics systems, we call it to be. So as a part of it, the key objective is very clear cut. There is we are trying to bring about zero manufacturing, zero defect manufacturing, which means that we are aiming for something perfection in every product that we produce. Okay, every product that is coming out, say for instance a car manufacturing organization like an BMW or Tesla, everybody is interested with zero defect, because perfection is very important, because it is no compromise on the product quality. So next is just in time production. This is very important in the assembly line of the CPS manufacturing. So everything arrives exactly when it is needed. That is what we call it to be just in time production. Next you have the maximum flexibility. So this maximum flexibility is the now if I'm upgrading, if it is a car manufacturing sector, we will have a model, upgraded model of the car rolled out every year, so that I cannot change the complete factory floor. Only that is that I can, my factory floor has to be flexible. So that is the ability to switch between different models as possible. So that is important. Next is the energy efficiency, the smart use of resources. That is very important because these same manufacturing sector are very much interested with the energy efficiency and sustainable operations, which is leading or which is going to be the next era, sustainable operations. So how environmentally we are responsible, that is, I'm just reiterating it. So these are the key objectives when you're trying to introduce CPS in the automotive manufacturing sector. Okay, so as we have seen earlier, the layer that are available in the CPS architecture, the physical, cyber, and the network. So very quickly, if it is an automotive manufacturing sector, the physical layer would be having the hands-on components like your robotic assembly systems, your the task handled by it would be welding task. A robotic assembly system will be taking up the painting application task, or the assembly line robot, anything it can be. So these are the first thing is that you will have in an automotive manufacturing sector, you will have robotic assembly systems. You will have quality inspection systems. So quality inspection is something like we are working on recently. In almost all the industries have come with vision based systems for quality inspections. So you will be having pattern recognition algorithms or vision based algorithms working in hand with AI to identify the quality inspections. So next is the material handling systems, which will include your automated guided vehicles, your AGVs, smart conveyor systems, all be part of the material handling systems. So these will comprise the physical layer in a typical automotive industry manufacturing sector. So moving up, we have the cyber layer. This is where something like I told you, brains of the operations live. So that which is the core component. So you have the first thing is that your MES, that is your manufacturing execution systems. So handling your production scheduling, resource management, plant control systems, everything which is including your PLC, SCADA, industrial PC. Everything is coming under this picture of the plant control systems. Next, you have data analytics platforms, which is having the sophisticated analytic platforms like your real-time analytics, predictive maintenance, and the quality predictions. And next apart, going further, is that we have to talk about the nervous system. As I told earlier, it is the is this layer which is going to connect all together. Everything is going to getting interlinked. So first you have the industrial networks. So as listed earlier, you have the industrial Ethernet, you have the OPC UA, you have the Profinet. So all these industrial communications, wireless systems, your data management entities, all comes under the category of, or the under the roof of network layer. Now, typically, I will let you know a paint shop application or a functionality which is very much very much available or a basic functionality that everybody would be understanding. So I'll take up this paint shop systems and explain you the CPS applications and the machine learning on the digital twin technologies, how it is being deployed in the automotive industry under the functionality of paint shop. So when it comes to CPS, so as I told you, this paint shop is a critical stage in the automotive manufacturing, where you are trying to have your vehicle's exterior final color. So this is very basic thing that we are taking. So first thing, how your cyber physical getting integrated here. So first is you can have the real-time data integrated. So your CPS is going to integrate your machines, robots, sensors in the paint shop with a centralized digital network. So what happens is that you can have a real-time monitoring, control of the process. You can have the optimal performance. Okay, everything done or everything is monitored over remotely. Okay, so next you have the for this implementation you have the IoT sensors. So these sensors are going to collect the data from various parts of the paint shop operations. Say for instance, you will be deploying a temperature sensor, a humidity sensor, spray pressure sensor, and you can understand what has to be altered if you have to go for a changing color, or if you want to go for a better quality of the paint that has to be applied to the exterior. All actionable insights can be taken up. So that is the point of CPS getting involved. So next, when you see in the perspective of Industry 4.2, artificial and the machine learning is very important. So getting into the paint shop application or the functionality, the first thing is that you have predictive quality control. Now your AI algorithm is going to analyze the data, because when it comes to quality control, as I told you, vision system is going to get involved. So vision system along with this machine learning model is going to detect the defect, so that you are trying to identify proactively the quality issues. So you can so further you can just have an alteration in your process, or make it flexible so that you achieve the better product quality is available for you. Next is energy efficiency. So when you are working, your AI is going to help in optimizing your energy consumption, because you have the curing ovens that is going to operate at maximum efficiency. You have to reduce the waste and the cost. So in that perspective of the paint shop applications, your energy efficiency also is being improved when you are trying to integrate AI or machine learning. Next is your digital twin technology. So as I told you, it's a virtual replica or virtual model that you create. So now, when you are trying to create a virtual model for the paint shop, now you can simulate your process and you can see virtually what is its outcome. So now you're not trying to test it on a real car or a real entity, but rather you are just trying to have test it on a virtual platform and see what are the changes that is required when you go for the actual process of paint shop application. And somewhere you are just your digital twin technology is also helping in equipment failures identification also. So which means your downtime gets reduced, which is your chances of unplanned downtime reduction is another important thing to be noted, because not only paint shop, in any other functionality of the manufacturing sector, you will have to have this key thing to work on, that is your digital twin technology is aiding this predictive maintenance. The next is the, okay, this is another functionality that is in the automotive industry, that is the final assembly integration. Again, in the final assembly integration or the quality checks, we have multiple entities or the core components of industry 4.0 being getting integrated, your CPS, AI, automated guided vehicles. So when it comes to human machine collaboration, we have all these are going to enhance. So you have under the roof of cyber physical systems, you have IoT and predictive maintenance, which is going to aid in the final assembly integration. So these are the technologies of Industry 4.2, which is going to aid in various functionalities of the automotive manufacturing sector. So I'm just I'm just watching up through these slides. We are just nearing the time of completion. So just quickly into data integration and analytics. So in modern manufacturing, data integration analytics also plays an important role. So not only collecting the data, so your resources, data sources can be anything. It can be a process data or a sensor data or a quality data, whichever is there. We have to store it, and we should go for analytics. So that is the important thing. So when it comes to analytics, you have two categories of analytics. One is the descriptive analytics and another is the predictive analytics. So when it comes to descriptive analytics, it's something like what has happened, how well did the manufacturing process perform. So all that visualization that you can have is the descriptive analytics. So if you are able to take from the history of data, if you are able to build through an machine learning model or an time series forecasting algorithm, predict the future outcomes. Okay, so then it becomes the predictive analytics. In either cases, you are making use of the data that is coming out of the factory floor. So two types of analytics has to be done. So these are the in the automotive sector, how your analytics are used. Okay, I'm just quickly skipping off this process industry application because it is quite repetitive. Be it any manufacturing sector, the core characteristics and the key objectives are going to more or less remain the same. So these are the same in an industry. I mean, in an chemical manufacturing sector, what are the? You have some additional entities like your safety systems, you have fire and gas detection. So there are some alterations, but then your apart from your physical layer and the safety systems, all would remain the same, because for be it any manufacturing system or any factory floor, the basic architecture is this 3-layer integration and the technologies. So future trends. So that is what everybody is looking for. The future trends is, first one is AI driven manufacturing. So you have this is a very big topic of research. So somebody is working on Industry 4.0 or industry automation. They can think of AI driven manufacturing, and these are the roofs under which it is being deployed. So machine learning applications, you can see it has been wide scope is there in predictive quality control, adaptive process control, resource optimization. You have deep learning models for visual inspection, anomaly detection, fault analysis, pattern recognition, all that things. Next, you have AI decision support for real-time optimization, autonomy decision making, performance prediction. So this is how largely, by large, your AI-driven manufacturing technologies are driving forward. Next, you have digital twin technologies. So digital twin applications you will see in production system twins, product twins, and real-time integration. So these are the other applications where you can see the emerging technology of digital twin is being applied. So under the production system twin, you have the virtual factory modeling, process simulation, layout optimization, all under the head of production system twins. And the product twins, you have design validation. So you are trying to have a product twin. So design validation, testing the performance, quality predictions, okay, life cycle management, everything comes under product twin. Real time integration is like kind of live data synchronization with the model that you created. Predictive maintenance, process optimization, all will facilitated by this digital twin application under the real-time integration process. Next is extended reality. So very much you have another possibility in the production line is the extended reality. You have as a part of extended reality, you have the AR, VR, and the mixed reality. So supporting various forms in the industry improvements. Next, you have the autonomous production systems. So you have self-organizing systems, autonomous operations. When it comes to autonomous operations, you have the robotics, the automated guided vehicles, and smart integration. You have the system coordination, real-time optimization, error recovery. Everything comes under the roof of autonomous production systems. Next is the future trends. This is quite interesting. We have seen the emerging technologies like what is the phase of implementation of the CPS in the manufacturing, but you have implementation challenges. So although these emerging technologies are up, you have the implementation challenges, be it system integration, because you will have an legacy system you are trying to connect it to a modern factory setup, then it is very challenging. Your standards and protocols may differ. So since it is CBS, you should have you're trying to transmit a sensitive manufacturing data. So in that very much important aspect that one has to look for is the data security, data privacy, because it is the organization's data and the compliance. So that is the part of other challenge in implementation. So this is the operation challenges. If you see, you have the security concerns, as I told you, the build. You have the workforce adaptation. So workforce adaptation is something like you are moving from a different environment of the factory to a modernized one. So you have train your workers or the operators. So there you have workforce adaptation is required. So there is a lot of training for enhancing the skill has to be there. So all that are the implementation issues or the challenges we should talk about. So as the conclusion, I can just tell we are looking for something like Factory 2.0 that is going to represent the next evolution. So this is how it is all progressing towards. So where you can have automated decision making, self-optimizing systems, zero defect production, adaptive manufacturing, just being very flexible. And we are moving into this is which is very much important, because next we are very cautious about the sustainable operations. So we have carbon neutral process, circular economy, resource and the energy optimization playing a great role in future. Okay, so that is the future of the manufacturing sector. At large, we have the connected ecosystem, emphasizing the broader integration and the collaboration. So you have the supply chain integration, platform economies, and global synchronization, all coordinated worldwide integration operations. So this is how the future manufacturing will combine the intelligence, which is called to be the industry smart factory 2.0, your sustainable operations and connectivity all together, which is be creating a more efficient, a more environmentally responsible, and something like a globally integrated manufacturing system. So I suppose I'm done on time. Sorry, I have sorry, it's like 10 minutes out. Okay, I'm done with the presentation or the lecture for this topic. If any queries, we can go ahead.
Thank you, ma'am. Thank you, ma'am. Any questions
Yes.
from my side? It is a great honor and privilege to extend the vote of thanks for this insightful and engaging session on behalf of management and Department of EEE. I would like to express our sincere gratitude to Dr. Ravadi ma'am for her expertise on industrial cyber physical system integration, advancing smart manufacturing for Industry 4.0. So her presentation provided us with a comprehensive understanding of how these advanced technologies are shaping the future of smart factories. Thank you, ma'am. We are truly grateful for her valuable time and knowledge she has shared with us today. Finally, a special thank you to our audience for your active participation and engagement. Your involvement added very great value to this session. Thank you all once again. Thank you, ma'am.
Will be joined tomorrow.
So we'll be joined tomorrow, the session, day 4 at 6 p.m. Thank you all.
Thank you, ma'am. Thank you all.